All right. For chapter number 7, how far, how fast, the next topic we have at hand is activation energy. Now, the minimum amount of energy we require to start a reaction or to jumpstart a reaction is known as activation energy. There are many examples for which we can usually quote that, but for the burning of fuels, we have the easiest example of all. When fuels are burned, energy is needed to ignite them. Now, in order to start the whole fire, the energy may come from a spark, it may come from a matchstick, it may come from sunlight, it may come from anything. That minimum amount of energy to start the whole reaction is known as activation energy. The symbol is going to be EA, both E and A are in caps. It is required because initially some bond must be broken before any reaction can take place, right? So this energy, when coded in our energy profile diagrams, change them a little bit. Now, this is an energy profile diagram for an exothermic reaction, right? How do we know it's an exothermic reaction? It's pretty easy. Remember, we give you 3 pointers for it. The reactants are going to be at a higher energy level. The product, I'm going to extrapolate it a little bit. The products are supposed to be present at a lower energy level. And then we have an arrow that shows that energy is given out. Now, this is the heat of combustion. Although there are double arrows over here, but I ask my students that this is now a notebook. If you actually check the newer version of the book, you would notice they're not using double arrows anymore. They're not using this one. They're not using this one. Instead, they use an upward arrow over here and they use a downward arrow over here. Now let's clarify. This arrow is upward because the value of activation energy is always in positive. And keep that fact in mind. Instead, it's better to write that fact on the hard copy of your book so that you always remember activation energy value is always going to be positive. It's never negative, which means this energy will always be absorbed, never given out. Make sure you write it on the book. Now, moving on, the other arrow is face downward because that's the heat of reaction or the enthalpy change or what we commonly call heat of combustion. This is the heat which this reaction usually gives out. Since we're burning a fuel, so it's bound to give out some heat. This is that heat. Make sense?
Yes, sir.
All right. Unfortunately, this book does not contain the energy profile diagram, including activation energy for endothermic reaction. So let's draw one. So in the similar way like this one is, and I am going to go for a shortened version for this one. So we're going to go for the same graph. On the x-axis, we have progress of reaction, right? In the same way, since I don't have enough space, so instead of writing it below the x-axis, I'm writing it on one side of it. And on y-axis, we have the same energy. And energy is, as usual, always taken in kilojoule or kilojoule per mole. Now, since we are talking about an endothermic reaction, so we're going to quote the reactants over here, whichever reactant those are. We can even take the example of nitrogen and oxygen converting into NO like we did previously, or we can take any other example and products over here. All right. This clearly gives the idea that the reactants have low energy, the products have high energy, and we can put a dotted line over here, a dotted line over here, and in order to give the idea, we can actually have a straight arrow upwards. Instead of dividing this arrow into two parts like we did with exothermic reaction, for endothermic reaction, we can use a straight single arrow and it would be faced upwards. To be honest, this part is activation energy and this part is delta H, but this whole is taken as activation energy. This whole is taken as activation energy because of a reason, and this might make complete sense to you when I say it, that this entire amount of energy, be it the heat of reaction or the heat required to convert the reactant into product, as well as the activation energy, the combined energy is required for the reactants to be converted into products. Hence, we call this whole as an activation energy. And this would make sense because if we don't give any part of this energy, be the heat of reaction, be the activation energy, the reactants will not be converted into products. Since that wouldn't happen, so we need to understand the fact that this whole can also be taken as activation energy. Well, that's one way of putting it. Are we good?
Yes, sir.
This graph is present in the next version of this book. This is the fourth edition of this book. If you take a look at the fifth edition of the book, this graph, which I'm drawing right now for endothermic reaction, is given as a part of that book. But since it's missing in this edition, that's why I drew it separately. I hope you have copied it already, right?
Just a second, sir.
Okay, let me know whenever you are ready. I'm gonna erase it and move to the next page. So let's clear it up. The next topic we have is rates of reaction. Now, in case of rates of reaction, we understand that many reactions are too slow and many reactions are too fast. If I talk about too fast of reactions, any kind of explosions, burning of fuels are usually very fast reactions. If I talk about slow reactions, then as they've just given the example of a submarine or a ship, the shipwreck or the corrosion or rusting of iron, for that matter, is a slow reaction. It takes a few days. So there are some reactions which happens in seconds. Some takes minutes, some takes hours, some even takes days or weeks to complete. So reactions can even be very fast, can be moderate, can be really slow. So the rate of reaction is all about speed of reaction. Rate and speed means the same thing. When we use the word in rate, remember the word in rate, according to physics, means that we are taking some measure as a numerator and dividing it by time as a part of denominator. Here, we're talking about progress of reaction as a numerator, and we're taking that progress of reaction over time as a denominator, and that's what we call rate of reaction. Now, rate of reaction can easily be considered as speed of reaction, and the same thing is mentioned over here. There are many factors which affect them. Considering those factors, in this book, we are going to go with many. We'll be considering surface area of solid reactant. Remember, surface area is a factor which will only be effective in case of solid reactant. Concentration in case of any kind of reactant, temperature at which the reaction is carried out, the use of a catalyst, the influence of light on some specific reactions, which obviously get affected by light. Here we'll discuss photochemical reactions. Photosynthesis is one of the examples, since you are already familiar with the word and the reaction, so this would make sense to you. And since there are other factors as well, they haven't actually noted it over here, so I ask my students to uh, keep on going with the list, and the next point would be pressure slash volume of gaseous reactants. Since we're talking about surface area for specifically solid reactants, so if we're going to talk about gaseous reactants, then we're going to talk about specifically pressure or volume. Keep on with the list, and the next point would be time. This goes for all kind of reactants and all reactions. How does time and rate of reaction actually conform one another? Are they directly proportional? Are they inversely proportional? How do each one affect the rest? all right? So we're going to go with not just the 5 factors mentioned over here. Instead, we're going to take under consideration 7 factors. And all 7 of these have been considered in past papers. So when you're going to go through the past papers, you won't have a problem if you understand not just 5, all 7 of these factors. Let's start with them one by one. These factors, which I've noted up top, are also part of the same book we're doing, but they haven't been given as a heading over here. We're going to go through them as a separate heading, right? Let's start with the first one in the book, the surface area of solid reactants. Now, if one or more of your reactants are solid, now the surface area can be deferred by many different ways. We can take finely divided powder, finely divided solids. We can take their larger lumps or pieces. So it is actually going to be different surface area. Solid has a much larger surface area when it is powdered, or it has a much smaller surface area when it is in larger pieces. So this is going to be a different rate of reaction. Let's consider. Let's take a good demonstration. You can see the apparatus that we are about to handle. As you can see, we have a wing balance. On top of it, we have a conical flask. In that flask, we have some marble chips, some dilute hydrochloric acid. There is some cotton wool to stop acid spray or any kind of spill of acid. Or if the acid tries to escape, we definitely are going to use a stop block or a stopwatch. The reaction can be given as calcium carbonate plus hydrochloric acid. As back from chapter number 5, you already know it's going to give us a salt, calcium chloride. It's going to give us water. Along with it, it's going to give us carbon dioxide. Now, this is a very good example of a reaction that consists of all 4 state symbols. Take a look at it. You have a solid state symbol, you have an aqueous state symbol, you have a liquid state symbol, you have a gaseous state symbol. Now, this really gives you a very good idea that carbon dioxide, being the gas, is one of the products. Now, if I talk about this whole setup, notice that when we start with marble chips and dilute hydrochloric acid, they'll have a specific weighting start. But when the reaction proceeds, it gives out some gas, the gas would be able to escape through this cotton wool. Although there won't be any spray of acid, will be completely safe from any kind of spills, but the gas can definitely leave the system. So if initially you start off with a bigger value for mass, you're going to end up with a smaller value. This kind of experiment is commonly considered as a loss in mass experiment because you start off with a higher value since the reactants have a higher value in mass, and as one of the products, being gas, leaves the system, the mass decreases, hence the term loss in mass. We are going to take this loss in mass, we're going to put it against time as we have the stopwatch over here, and that's how we're going to come up with our graph. We're going to perform, or you can say re-perform this experiment in 2 separate ways, or maybe 3 separate ways. In order to clarify that, let's move on to the graph that we have for this experiment on the next page. Figure 7.15. This graph shows the loss in mass against time for experiments A and B. The experiment A, as shown in the graph, is with the large chips of marble. The experiment B, on the other hand, is with small chips of marble. We have the time in minutes on x-axis, and we have the loss in mass in grams on y-axis. You'd notice that when we start the experiment, we start getting some loss in mass, and the loss in mass is less than 2 grams. Since the gas does not weigh too much, there would be very small values for the loss in mass experiment, but even those values can give us a really good idea of what happened in our experiment. All right. So notice that the reaction is pretty fast in case of small chips. It's fast, and it's slow in case of large chips. How do we know? This slope that you can see, if it's closer to x-axis, that means it's slow. And if this slope is getting steeper, or in other words, it's closer to y-axis, all right, we are going to take it as faster. Do you get the point? That's how we read this graph. Now, obviously, there is a reason behind it. We're going to discuss the reason, but first, the basic understanding. The steeper this curve is going to get, the more steep the curve, the faster the rate of reaction. The less steep the curve, this is less steep, and that means it's slower. Okay, so let's clarify. We are actually explained the whole curve that we usually get in the graph by what is happening in the reaction. Now, this is a deeper detail of what's actually happening in the reaction or why the reaction is behaving differently at different points. We should start at the bottom. It gives us the idea that the reaction is fastest at the start. We have a large change in the amount of product in a very small amount of time. Why? Because the reason, which is not mentioned over here, is that we have maximum amount of reactant present. And when you have maximum amount of reactants present, the speed is definitely the fastest, right? That's what happens when we have maximum energy. This is exactly like the same, like a race in a athletic game, or like what happens to a student at the start of the homework, since he has the maximum energy at the start of a race, or he has the maximum energy at the start of a homework, he's definitely going to go with a higher pace. Imagine yourself sitting in the exam. At the start of the exam, your speed is fastest. Why? Because you have the maximum energy. Of course, you're going to go fastest at the start. So this must make total sense to you. Now, moving on, we see that this slope starts becoming less and less steep. Instead of going straight up, this starts to flatten down. So we have other points. Apart from this point, which we have over here, we have 4 more points that have been probably explained for this graph. This one tells us that the reaction is slowing down. Now we're getting smaller change in the amount of product over a larger period of time. Why? Because the reactants are consumed up. Not consumed up completely, but a major portion of the reactants are consumed up. So of course, it's going to start slowing down. Moreover, we have the next part, this one. If I mark this one as 1, this one as 2, this one as 3, the 3 tells you now the curve really starts to flatten down. And it is starting to become parallel to x-axis. Now we have a very small change in amount of product over a larger period of time. And soon after this point 3, you have point 4, in which there is no product form. You get a straight line, exactly parallel to x-axis. This means the reaction has finished. So the reaction is started fastest at the start, point 1. It slows down, point 2. Reaction is about to finish, is point 3, about to finish. That's how we describe point 3. And the reaction is finished, point 4, after which we get a straight line parallel to x-axis. And this definitely has everything to do with the amount of reactants present. Since the amount of reactants present is maximum at start, it's fastest at start. Since the amount of reactants is almost consumed up at the end, so the reaction is about to finish at the end. So the amount of reactants present at any time in the reaction mixture is actually something which decides what the speed of reaction is going to be. Does that make sense? Can you hear me? All right, so this should give you the idea about it. Now, before I make any changes to this graph and further study this graph, I'm going to write a few points. Now, in this case, what happens is that the particle size, the surface area, can you hear me?
Yes, sir.
Right, my bad, a little bit problem in the internet. So coming back to it, particle size, surface area, and we're going to discuss uh, the rate of reaction. Now I'm going to connect all three of these in a single place, which would give you the idea about how we talk about when we talk about chips, what kind of surface area they have, or how the rate of reaction would be. So that would actually clarify everything. And before I make any changes to this graph, this table is going to help you to make changes to the graph positively. Now, when the particle size is large, let's say we're talking about large chip, surface area would be smaller or small, and the rate of reaction would be slower, right? When we change the particle size and we go for small chip, instead, in another experiment, the surface area becomes moderate, and of course, the rate of reaction also becomes moderate or mediocre. Now, in order to fasten it up, what we can do is that we can go for powdered system in which the particle size is definitely very small, but the surface area is large at that point, and the rate of reaction is faster at that point. So that's how it goes. So if I have to draw, and that's a pretty common question by Cambridge, if I have to draw another curve on this graph, and most probably you're going to face this question in paper 4 theory, or paper 6 has a very good history of these kind of questions, ATP. So you will see, notice that I'm going to actually move this up a little bit so that I can show you the whole graph. Okay, but I'll have to actually, let's go with a different color. Uh, let's go with green. So if I have to draw another graph, another experiment with C, that's probably how it's going to go. And that green is actually going to go like this. Okay. So this green would be C, and the C would be powdered, right? So if Cambridge comes up with particle sizes, and they may come up with many different categories, not just three, large, small, and powdered are not the only categories they think that they can go for. Of course, they can come up with size and figures. They may come up with 2 centimeter size, 1 centimeter size, 5 millimeter size. 3 millimeter size, 1 millimeter size. They can, of course, come up with any numbers to give you the idea. Remember, the larger the particle size, the more the graph is going to be towards the x-axis and less steep. The smaller the particle size, the more steeper the graph is going to be and closer to the y-axis. And since we've already discussed, I hope you remember my previous point, the more the graph goes towards the x-axis, the slower the graph gets. I mean, the rate of reaction, of course, from the graph. And if the more it's going to go towards y-axis, the faster the whole rate of reaction system is about to be. Because understand, we're going to jump up the values straight in the first few minutes of the graph. How do we get to know that? You can do an easy assessment. Let me compare all three of these for you. And this time we're going to use black. Okay. So I'm going to draw straight lines. Let's say that we consider the point at 2 minutes for all three of these graphs. Now I'm going to clarify myself by drawing simple straight lines for this one and for this one and for this one. Let's go with the straight line for 2 minutes. And if you extrapolate these lines to the y-axis, this is what this one comes out to be. This is what this one comes out to be. And this is what this one comes out to be. Okay. So notice this is experiment A's result. This is experiment B's result. This is experiment C's result in just first 2 minutes of the graph. So experiment A has probably just produced 1.07 or something. Let's say it's 1.07, it's 1.58, it's 1. I guess 91. These are the values in grams of loss in mass for just first 2 minutes. Although I hope you understand this is 1.95 as the last value in grams. So imagine how closer to these values are in just the first 2 minutes of this reaction, although there is a 7-minute graph drawn over here. So this is the amount of time they are going to take. And if you compare all three of these to become flattened, you'd notice that the blue flattens over here. The blue flattens over here, which is approximately 5.5 minutes. The red flattens almost at 4 minutes. And as per what I've done over here, the green already flattens at 2 minutes. So the reaction is almost up to completion in 5.5 minutes for large ship, 4 minutes for the smaller ships, and of course for powder, the reaction is almost up to completion in first 2 minutes only. It doesn't even take that much time. Why? It has a higher speed. That's why. Which definitely gives you an idea that faster rate of reaction is actually lesser time to complete, right? And slower the rate of reaction, more time it's going to take to complete the reaction. That's how we perceive rate of reaction. So if you get a rate of reaction idea at the very first graph, how these number works, what does these graph mean, what is the flattening of this whole line mean, you would easily be able to assess for the examiner about the rate of reaction, faster, slower, moderate, as per the particle size, large chip, small chip, powdered, or as per the surface area, whether the surface area is going to be smaller or going to be moderate or going to be larger. You're going to get all of those points. And if he asks you to what happens in the first 2 minutes of the reaction, or when does the reaction is almost up to completion, when there is no change in the amount of products afterwards, you know when the reaction is about to complete. No matter how bigger a graph you have been shown, you can always work out when the line starts to flatten, and that's the point when the reaction is almost up to completion. I hope this whole thing makes sense to you. Are we good? So what I'm going to do is that I'm going to take a picture of this. I'm going to share the picture. Of course, you're going to get the recording too. So can I clear it up? Right, let's see. So he discusses the same thing over here. He discusses why we put the loose cotton wool for the spring out of acid. Maybe at point times there can be spillage, but it is actually bad for us. The reaction's fastest at the start. Why? How does it get slow? So the total volume of gas released and the rate of reaction increases when the surface area of solid reactant is increased or a smaller particle size is used, which means I hope you understand that the rate of reaction and surface area and particle size, how do they actually relate to one another? So the rate of reaction is faster if the surface area is larger, if the particle size is smaller. That's how they relate with one another, right? And the rate of reaction would be slower when the surface area is smaller and the particle size is larger. The particle size and rate of reaction are inversely proportional to one another. If the value of one increases, the other one decreases, of course, and vice versa. But surface area and rate of reaction are directly proportional to one another. Larger the surface area, faster the rate of reaction, and vice versa. So I hope this gives you a very good idea about it. Again, let's clear it up. Let's move forward. Can I clear it up? This actually concludes our whole experiment. The first factor of surface area of solid reactant and how that affects the rate of reaction. So let's clear it up. Let's move forward. Next point would be the concentration of reactants. Now, we aren't talking about anything in specific when we're using the word concentration, right? So this really can be anything. Concentration means the amount of reactant. In simple terms, the amount can be discussed in different ways. You can take the solid ones in grams, the liquids or gases in their volumes. The concentration can also be taken for the word in terms of solutions. So that really is a bigger, broader term. And in this experiment this time, we're going to go with an experiment of acid along with a metal. Now, this is the diagram, figure 7.17 for this specific experiment. Take a look, we have a flask, and in that flask, we have a glass wall that divides the flask in two. On one end, we have the excess dilute hydrochloric acid. Of course, we're going to change the concentration of this hydrochloric acid to different experiments in order to make our point of the concentration of reactants. On the other hand, we will have the magnesium coil, or we can use the magnesium foil for this purpose as well. Now, we didn't leave it open this time or added a loose cotton plug. Instead, we put a cork, made it airtight, and we pass the delivery tube through this cork. The delivery tube connects to a gas syringe. Remember, the gas syringe is for the collection of gas. That means we definitely intend this time to collect some gas. And as soon as we collect the gas, the plunger is going to move out. So the plunger would keep moving outwards if the gas it would keep getting collected into it. We have a stop clock at the same time. Remember, if you're talking about rate of reaction, we're definitely going to measure it with respect to time. So when we measure it, let's go with this graph. This time we have the time in seconds on x-axis. So remember, if you have a faster reaction, you can change the unit to a smaller one in case of time. And if you have a slow reaction, you can use a bigger unit. So seconds, minutes, hours, days, weeks, it's entirely up to the speed of your reaction and the ease of performing those calculations and making a graph, right? We have the volume of hydrogen gas, which is the gas which is being collected in the gas syringe over here in cubic centimeter. Now, I hope you understand that there are measurements given on this gas syringe. So you will automatically get to know how many cubic centimeter of the gas we collected. Now, we have done two different experiments. Experiment C with 1 mole per decimeter cube, the concentration of our dilute hydrochloric acid, and D with half the concentration as compared to C, which is 0.5 mole per decimeter cube of dilute acid. Now, of course, higher the concentration, faster the rate of reaction, C, red line. Lower the concentration, lower the rate of reaction, D, blue line. Of course, would be less steep, C would be more steep. Now, if Cambridge gives you any third values and asks you to redraw the graph, this is you're about to do. Now, I'm going to use a different color this time. So if they give you any value less than, let's say they give you 0.25 mole per decimeter cube. Of course, that's the task. That means the value is going to be even less than this one, below blue line, and then it touches afterwards. It may even go out of this graph. It doesn't even touch in this graph. That can happen. Of course, we can have as slow or as fast the reaction could be. Now, if we talk about 0.75 mole per decimeter cube, then this is something right in between these blue and these red lines. Of course, this is going to be something over here. And if they come up with something like 2 mole per decimeter cube, all right, so definitely it's going to be even more steeper than this red line is. So no matter what kind of value they can come up with, you always have a way to draw the graph as per lower than your least steep line or higher than your most steep line, which means you can always go for drawing a slower or a faster graph as per the requirements of the examiner. I hope these lines give you an idea how slower or faster rate of reaction graphs or how less or more steep graphs can be drawn on top of what you already have as examples. Now, coming to the
Yes, sir.
conclusion of this experiment, since we have discussed all other parts on the previous graph was discussed in a lot big detail. Why? Because I had to go with the starting points, the basics, how to extrapolate the further values of graph, how to calculate which one was completed at what specific points in time or volume of hydrogen. Since that was loss in mass, that is somewhat different. But compared to this one, of course, the volume of gas collected in this case. So I'm not going to go with all those things in detail because we are done with that one. So of course, for any other graph, you can figure out the same stuff by a little bit of extrapolation. Let's say he asks you what is the value of rate of reaction for graph D at 50 seconds. Of course, you understand you're going to extrapolate it at 50 seconds and then over to the value of the y-axis, which would give you the idea that what the value would be for the volume of hydrogen at any specific point in time. So you can always work out and extrapolate the values. This whole connecting to the axis in dotted lines is known as extrapolation, and that's actually a term used in mathematics for graphs, and we use the same mathematics term here in chemistry. That's extrapolation for graphs, and any question related to that, be it related to extrapolating the line to x-axis or to y-axis or to both the axes, you can obviously do that. Okay, that's basically more of mathematics than it is of chemistry. So the results show that the rate or the speed of reaction increases when the concentration of any specific reactant in the solution is increased. So for solution, the concentration of reactant means, of course, the mole per decimeter cube or the mass per decimeter cube, mass or molar concentration. But apart from that, for any reactant, concentration can exactly be equal to the amount of reactant used. The more the amount, faster would be the rate of reaction. That goes for the masses of solids, or cubic centimeter values for gases or liquids, means the volume. So I hope you get the point, and I hope this simple conclusion gives you an idea what would happen in terms of concentration. So it's really very easy. Increase the concentration of the reactant, the speed of the reaction would increase. So concentrated acids are going to do better in terms of rate of reaction, and then the dilute ones. And the same thing is mentioned in these 3 points. This covers the first two factors for today. Actually, the first one was surface area of solid reactants. The second one is concentration of reactants. And I hope you're clear with both. Any questions?